Next, let's talk about speed up, which is a measure of performance for a parallel application. Suppose that you've designed a parallel application that consists of a large body of work. And now you're going to divide that up into pieces so you can run each one of them simultaneously in order to speed up the application. Now, you might be tempted when you start to run the application on as many cores as possible. Let's run it on 10. If not 10, why not 100? And if we can do 100, why not 1,000? Where do we stop? To decide how big to run the application, we need to have a measure that tells us how well we are doing, and this measure is called speed up. So to explain speed up, I'm going to draw a little graph. And on this graph, we're going to put on the x-axis the number of cores that we're going to run an application on. And on the y-axis, we're going to put the runtime. Now, whenever you evaluate the performance of a parallel application, you want to start by looking at the performance that you get when you run that application on one core, so you have something to compare it against. So let's suppose we take this application and we run it on one core, and it takes about 1 hour to run at that scale. All right, so there's our baseline. Now let's take that application and run it on 2 cores. Ideally, it should run about twice as fast. So maybe our performance is about here. And we can go out to some larger and larger numbers. So we'll go out to 4 cores and then 8 cores. And then maybe our performance looks like this and like this. And as we get bigger and bigger, what typically happens is that improvement in performance gets less and less. Now, it turns out that this isn't the ideal way to look at it, because as our numbers get larger and larger here, our differences get smaller and smaller, and it's very difficult to decide what's going on. So instead of extending this graph all the way out, instead we're going to compute the opposite, which is known as speed up. And the speed up of a parallel application on n cores is defined as the runtime of that application on 1 core divided by the runtime of that parallel application on n cores. Now, ideally, that speed up is going to be exactly n. If I run it on 8 cores, I want it to be 8 times faster. And if I run it on 100 cores, I want it to be 100 times faster. But of course, that's not always going to happen. In fact, as n gets larger and larger, that is to say the number of cores you're going to run on gets larger and larger, your speed up starts to fall off. Now, obviously, a higher speed up is better. But we can also ask, how close are we to the ideal speed up? And this is defined as parallel efficiency. So the parallel efficiency is the speed up that we actually achieve at n divided by n itself, expressed as a percentage. And ideally, our parallel efficiency will be 100%. Now, you'll find that speed up is usually the metric that the user of the system is interested in, because the user wants the biggest speed up they can get, and they don't really care how many cores they're using as long as that number keeps getting bigger and bigger. But of course, if you get bigger and bigger and bigger and speed up starts to fall off, your parallel efficiency goes lower. And if you have a low parallel efficiency, you're wasting the machine that you're using. So it turns out that it's usually system administrators that are more interested in parallel efficiency. And they would like to see their systems used in a way such that parallel efficiency is very high. Now let's see what happens for a typical application as we scale it up. Let me draw a graph here that instead of showing runtime is going to show speed up as we increase the number of cores. Now, for the ideal application, if we run something on 1 core, then the speed up is going to be 1. That makes sense. And if we run it on 2 cores, the speed up is going to be 2 because it runs twice as fast. And so as we go out here, our ideal speed up is linear. Now, for a real application, we don't see this behavior. What we typically see for an application as n gets large is that the speed up starts out very close to the ideal, but eventually it starts to fall off, and it reaches some plateau. And we'll often call this the scalability limit of the application. Now, every application has a limit. Nothing can go on forever. But if it plateaus at a reasonably large number, we're satisfied that we have a scalable application. Now, unfortunately, not every application behaves this way. Sometimes you see the following behavior. As n increases, the scalability goes up, and then it reaches some plateau, and that's okay, but then it can start to go down. Okay? And so such an application has reached its scalability limit, but as we increase the number of cores, the performance gets worse. Now, why is that? There's a couple reasons. One is that as we increase the number of cores, we're increasing the communication between processes. And so the overhead of doing that communication outweighs any benefit from parallelizing the application. It could also be that when you're dealing with a batch system or some other piece of software, that the overhead of queuing and setting up the jobs then overcomes the benefit that you get from running it on multiple CPUs. So for every application, there's usually some ideal point here, which is the maximum scale of that application on that machine. And running on too many is going to make it worse. So the lesson is, you can't just keep adding CPUs. You have to look at the performance of what you get, and then make a decision about what's going to give you good speed up at a reasonable efficiency. Now, there's some other behavior that you should know about as well. There are some applications that can actually come above the line. So we'll see them do something like this. They start off with linear scalability, and then suddenly they jump up like that and go like that. Now that's very strange behavior. In fact, we call this superlinear scaling. Of course, everybody would love to have a program that has superlinear scaling, but it only occurs in some very rare circumstances. Usually what happens is that if you have an application whose I/O is disk-bound, as you increase the parallelization, the data assigned to each processor gets smaller and smaller, so now suddenly it fits in memory. And if each node can keep its data in memory, then it can run much faster than if it was keeping its data on disk. Now, another way to look at it is to say, once we are below this limit, the application couldn't function correctly at all. So ideally, this is something that you want that application to always be in that range of superlinear scalability. But don't expect to see that for every application. Now, the analysis that I've described here so far is known as strong scaling. And strong scaling is the idea that we're going to increase our system size while keeping the problem that we want to solve constant. This measures our ability to take one problem and solve it as quickly as possible. And this could be really important for something like, say, weather forecasting, where the sooner you can get the result for tomorrow's weather forecast, the better. Now, there are other problems that benefit from an analysis called weak scaling. And weak scaling is very similar, except that as we increase the system size, we're also going to increase the nature of the problem that we're trying to solve. Now, strong scaling isn't necessarily better than weak scaling. It's just a different way of thinking about a problem. With weak scaling, the problem that we're looking at grows with the machine. And so it's useful for sorts of analysis where you want to increase the resolution as you go. So perhaps you have a simulation that you'll get better results if you have better resolution, while weak scaling is the analysis that you want to do.